Welcome to my 47th tutoring session in A-level chemistry. In this video, I'll talk about the physical properties of halogens. Due to the extensive nature of the topic, I made this video in a two-part series. The current video focuses on the physical properties of halogens, while the part 2 discusses the chemical properties of halogens. Please take a moment to watch my previous videos on topics like dipole moment, electronegativity, van der Waals forces, shielding effect, and effective nuclear charge. These topics will provide you with a better understanding of this video content. Link to these videos given in the description below. Please do watch the videos. Kindly subscribe my channel, share, like, comment, and watch the full video. Now, more subscriptions and viewing time will motivate me to make many more interesting videos. So please do subscribe and watch the full video. Here's a simplified and condensed version of the periodic table of elements. Halogens belong to the 7th group, the periodic table. And I have color coded the elements, that is, the halogens belong to the 7th group. Halogens do not exist in the elemental form, rather they exist as diatomic molecules by sharing the electron pair. Here I have highlighted with respect to the iodine molecule. In case of iodine molecule, you can see that the two iodine atoms share the electron pair and as a result form a covalent bond. Now, halogen molecules are nonpolar in nature. They are nonpolar molecules because the atoms involved in the covalent bond formation, they are identical with same electronegativity values on the Pauling scale. So halogens are nonpolar molecules and exist as diatomic molecules by sharing electrons. And these nonpolar halogen molecules, they are held together by van der Waals forces. As you go down the group, the size of the halogen molecule increases. And as an outcome of increase in the relative size of halogen molecules as you go down the group, as depicted in this table, the first outcome is the variation in their physical properties like melting point and boiling point. With increase in relative size of the halogen molecules, as you go down the group, the melting point increases, the boiling point increases, and furthermore, there is a change in the physical state of the halogen molecules. Fluorine and chlorine molecules are gaseous in nature, while bromine is liquid in nature and iodine is a solid. Now, these changes in the physical state is due to variation in the strength of the intermolecular forces between the halogen molecules. So how does that variation in the strength of the intermolecular forces happen? Let's see the details. So as you go down the group, that is the group 7, to which the halogens belong to, the relative size of the halogens increases, and with the increase in the relative size of the halogen atoms, the internuclear distance also increases. So the internuclear distance in case of fluorine molecule is around 143 picometers, 199 picometers in case of chlorine, 228 picometers in case of bromine, and 266 picometers in case of iodine molecule. So the increase in the size of the halogen atoms, the internuclear distance also increases. As an outcome, there is a increase in the melting point, boiling point, and ultimately you can see the transformation in the physical changes. The physical state of the halogens changes with the increase in size of the halogen atoms. Now in case of fluorine molecule, you find a very weak intermolecular forces between the fluorine molecules because of its relatively small size, and as an outcome its density is low, it is gaseous in nature, and the fluorine molecules are not closely packed. In fact, they are loosely packed. The weak intermolecular force in between the halogen, the fluorine molecule, leads to the loose packing, and as a result it is gaseous in nature with low density. And what about chlorine molecules? Weak intermolecular force between chlorine molecules exist, leading to close packing of the chlorine molecules, leading to its low density and gaseous nature. But comparatively, the intermolecular forces are stronger in case of chlorine than fluorine. Even the packing is better as compared to fluorine. And what about bromine? A strong intermolecular force exists between bromine molecules, leading to a close packing, a relatively more close packing as compared to chlorine and fluorine, resulting in high density, and as an outcome, bromine is liquid in nature. So the intermolecular forces are stronger between bromine molecules as compared to chlorine and fluorine. Coming to the iodine molecule, very strong intermolecular forces exist between iodine molecules. As you can see in this diagram, the iodine molecules are very closely packed, and thereby it leads to a very high density, and they are solid in nature. And why there is variation in the intermolecular forces? Definitely the relative size of the halogen atom is one of the major factors. Additionally, what are the other supporting factors that leads to the variation in the intermolecular force between halogen molecules? So let me explain it. So as you go down the group, the size of the halogen atom increases. The increase in size is due to increase in the number of shells or energy levels in the respective atom. In case of fluorine atom, there are two shells or energy levels. In case of chlorine atom, there are three shells. In case of bromine, four shells. And in case of iodine, there are five energy levels or shells. With the increase in the number of shells, obviously, there is increase in the number of electrons. In case of fluorine atom, there are a total of 9 electrons in the respective shells or energy levels. That is the total number of electrons. In case of chlorine, you find 17 electrons. In case of bromine, you find a total of 35 electrons. And in case of iodine, which is a bulkier sized atom, you find a total of 53 electrons. So with the increase in size of the atom, the number of shells increase, and with the increase in the number of shells, the number of electrons also increases. So what is the outcome of this? The first outcome is that there is an increase in the shielding effect. What is shielding effect? Now, the inner core electrons, they partially block or reduce the electrostatic force of attraction between the positively charged nuclear protons and the negatively charged outermost valence electrons. This is called shielding effect. And as a cascading event, the effective nuclear charge decreases. What is the effective nuclear charge? As a result of the increased shielding effect, the electrostatic force of attraction between the positively charged nuclear protons and the negatively charged valence electrons, it decreases. So effective nuclear charge is the electrostatic force of attraction between the positively charged nuclear protons and the negatively charged outermost valence electrons. And the next outcome is the polarizability of the atom increases. So what is polarizability? Now, polarizability is a measure of how easily an electron cloud can be distorted by an atom or a molecule. Now, with the increase in the shielding effect and decrease in the effective nuclear charge, the nuclear protons loses control over the outermost valence electrons. That is in terms of electrostatic force of attraction. So the increase in the shielding effect and the decrease in the effective nuclear charge, the outermost valence electrons or the bonding pair of electrons in case of halogen molecules, it diminishes or reduces with increase in size of the halogen atom. And as a result, the electrons are distorted, resulting in dipole moment. And as an end result, the dipole moment generated in one halogen molecule, it induces a dipole in the neighboring or adjacent halogen molecule, leading to van der Waals forces or interaction. As the size of the atom increases, the van der Waals polarizability increases and the van der Waals force also increases. So polarizability is a chemical property that measures how easily an electric field can distort a molecule or atom's electron cloud. And this electric field, it can be induced or caused by a nearby ion, dipole or electrode. Here in the present case, it is the dipole. It is acting or contributing as an electric field. So this difference in the physical state of halogen molecules is due to variation in the intermolecular forces. So fluorine and chlorine molecules are gaseous in nature because of low or very weak intermolecular force between the fluorine and chlorine molecules, and that is why they are gaseous in nature. While bromine, the intermolecular force are a bit stronger, and therefore they exist as a liquid. While iodine is solid in nature because of its bulkier nature. So in case of iodine atom, the shielding effect is more, effective nuclear charge is less, polarizability is high, van der Waals force are high, and therefore, as an end result, iodine is solid in nature. So all these four factors go hand in hand, contributing towards the physical state of the halogen molecules. Now talking a little bit more about the polarizability of halogens. As you go down the group, the seventh group in the periodic table, you see the increase in size of halogens. Now in this particular diagram, I have highlighted only the nuclear protons and the outermost valence electrons. Remember, halogens have a total of 7 valence electrons. So I have highlighted only the nuclear protons of the respective halogens as well as the outermost 7 valence electrons. So as you go down the group from fluorine to iodine, you can see that the negatively charged electrons, outermost valence electrons, they are clustering towards one side of the atom. And as a result, you see a polarization of the atom or the respective halogen molecule. So as I already mentioned the definition of the polarizability. So polarizability is nothing but it's a measure of It's a measure of how easily an electron cloud of an atom or a molecule can be distorted. So this happens easily in case of iodine, but it happens with difficulty in case of fluorine atom. So in case of large atom, more distortion of electrons. So for example, in case of iodine atom, it is highly polarizable as compared to fluorine, chlorine and bromine. So in case of fluorine, there are two shells, the total of 9 electrons. Fluorine, 3 shells with a total of 17 electrons. And in case of bromine, 4 shells, the total of 35 electrons. And in case of iodine, 5 shells, the total of 53 electrons. Now in case of iodine atom, because of its bulkier size, the valence electrons are loosely held, and as a result, polarizability of the atom is favorable. It increases, a temporary dipole moment arises, and this leads to increase in strength of intermolecular van der Waals forces. Now so far our discussion is focused only with respect to the atom. Now let us discuss with respect to the halogen molecule, because as we know, halogens, they do not exist in the elemental form, that is atomic form. In fact, they exist in the diatomic molecular form by sharing of electrons. Now with the increase in size of the atom, the distance between the nucleus and the outermost valence electrons, it increases, and therefore the nuclear protons, which are positively charged, it loses control over the outermost valence electrons. Now little bit more about the electron structure and bond strength of halogen atoms and molecules. As you go down the group, the size of the halogen atom increases. So with the increase in size, there is increase in the number of shells. With the increase in number of shells, there is increase in number of electrons. And with the increase in the number of electrons, the shielding effect increases, effective nuclear charge decreases, electronegativity also decreases. Now in case of the fluorine molecule, the shared pair of electron is equally attracted by both the nuclear protons of the respective fluorine atom. So the shared pair of bonding electrons in case of fluorine, chlorine, bromine and iodine is equally attracted towards the respective nuclear protons. And that is what is holding the atoms together, keeping the molecule in a neutral form and stable form. Now with the increase in size of the halogen atom, there is an increase in the internuclear distance. So you'll find increase in the internuclear distance, as well as there is increase in the distance between the nuclear protons and the shared pair of bonding electrons. So as you go down the group from fluorine to iodine, you can see that the distance between the nuclear protons and the shared pair of bonding electrons increases. So with the increase in the distance, the electrostatic force of attraction between the positively charged nuclear protons and the negatively charged shared pair of bonding electrons, it diminishes or weakens. And as a result, the shared pair of bonding electrons are loosely held, and thereby the bond strength weakens or it decreases down the group. So now the valence electrons are loosely held, that are actively participating in the bond formation between the halogen atoms. The polarizability of the molecule increases, a temporary dipole moment arises, and there is an increase in the strength of the intermolecular van der Waals forces. So the strength of the covalent bond decreases, and the van der Waals force increases as you go down the group. Now a little bit more details about the covalent bond strength as you go down the group. Now the strength of the covalent bond decreases down the group while the van der Waals forces increase. So one needs to bear in mind these two highlighting points about the halogens as you go down the group. The bond strength decreases down the group while the van der Waals forces increase. So one needs to remember these 2 points when talking about the physical properties of halogens. Now remember the shared pair or the bonding pair of electrons between the halogen atoms is attracted equally to both the nucleus, and that is what is holding the halogen molecule together in a stable and neutral form. Now there are 2 aspects here. So one aspect is the strength of the covalent bond. The second aspect is the strength of the van der Waals force. Now the variation in the physical state of the halogen molecule is due to variation in these 2 aspects or these 2 parameters. That is the strength of the covalent bond and the strength of the van der Waals force. So in case of fluorine molecule, the covalent bonds are stronger while the van der Waals force that is holding the molecules together, they are weaker. So the covalent bonds holds the atom together while the van der Waals force holds the molecules together. Now why the covalent bonds are stronger in case of fluorine molecule? Because there are only 2 shells energy levels in case of fluorine atom, and therefore the nuclear protons in case of fluorine, they have easy access to the shared pair of bonding electrons. So what I'm trying to tell you is that there is strong electrostatic force of attraction between the nuclear protons and the shared pair of bonding electrons in case of fluorine atom because of the relative small size of the fluorine atom and reduced number of shells or the energy levels. And this leads to a strong covalent bond in case of fluorine. But as you go down the group, the distance between the nuclear protons and the shared pair of bonding electron increases, and as a result, the bond strength weakens, or the strength of the covalent bond decreases. So the strong covalent bonds hold the atoms of each molecule together, but the van der Waals forces which holds the molecules together are relatively weak as you go down the group. And therefore fluorine has low melting and boiling point, while iodine molecule has a high melting and boiling points. Now why fluorine and chlorine are gas at room temperature and pressure, while bromine is liquid and iodine? As bromine is a liquid while iodine is a solid at the same conditions. So let's summarize. As you go down the group, there is increase in size of the atom, and this leads to increase in number of shells. And with the increase in number of shells, the atomic radius also increases. So atomic radius is 64 picometers in case of fluorine, 99 in case of chlorine, 111 in case of bromine, and 128 picometers in case of iodine. So this leads to increase in the number of electrons. So 9 electrons in case of fluorine, 17 electrons in case of chlorine, 35 electrons in case of bromine, and 53 electrons in case of iodine. So this leads to increase in the polarizability of the molecule, and as a result, a temporary dipole moment arises due to random movement of electrons. So let me explain, considering iodine as a representative example. So here's the Lewis dot structure of iodine molecule, where you find the symmetrical distribution of electrons around both the iodine atoms. But due to temporary dipole moment that is created due to polarizability of iodine molecule, you can see a partial positive charge and negative charge generated in the iodine atoms. and as a result, the temporary dipole in one molecule attracts the opposite end of the neighboring molecule. So this leads to increase in the strength of intermolecular force, that is the van der Waals force, and more heat energy is needed to overcome these forces, especially in case of iodine molecule. Now these intermolecular forces can be overcome by providing heat energy, that is the thermal energy. So that is the reason fluorine and chlorine are gases at room temperature and pressure, while bromine is liquid and iodine is a solid. So what is the key takeaway from the discussion so far? Now the key takeaway is that the difference in the physical state of halogen molecules is due to variations in the strength in the intermolecular force between the halogen molecules. So it is the difference in the variations in the strength of the intermolecular forces that leads to the different physical state of the halogen molecules. So that is why fluorine and chlorine are gaseous in nature, bromine is liquid, while iodine is solid. Now why iodine is a solid and not a liquid or gas? Now iodine doesn't exist in the elemental form, but rather it exists as a diatomic molecule by sharing electron pair. And that is how the iodine molecule is formed, by mutual sharing of electrons. And due to polarizability, a dipole moment is created. And electrostatic force of attraction between the molecules with opposite dipoles leads to stacking of the iodine molecules. Now the iodine molecules are stacked one over the other due to strong intermolecular forces, and that is why they exist as a solid. And more heat energy has to be provided in order to overcome this strong intermolecular force that exists between the iodine molecules, in order to convert the solid iodine into the vapor form of iodine. So when the thermal energy is provided, the intermolecular forces are overcome, and this allows the iodine to escape in the vapor form as individual iodine molecules. Now iodine is solid up to a temperature of 110 degree Celsius, and they are closely packed. At a particular temperature, these strong intermolecular forces are overcome, and there is separation of these iodine molecules. Now the closed packing is slightly disturbed, and with further rise in temperature, you can see that they are further loosely packed and they escape in the gaseous form, that is in the vapor form. On cooling, exactly the reverse process happens. So on cooling, what happens? The gaseous molecules that are loosely packed in the atmosphere, on cooling it removes the added heat energy and the intermolecular forces increase, resulting in solid iodine. So on heating, the thermal energy, it overcomes these intermolecular forces, leading to loose packing. And on cooling, it removes the added heat energy and the intermolecular force increases, resulting in solid iodine. Now in case of iodine, there is no intermittent liquid state. There is direct transformation of solid to the vapor form, that is sublimation. So sublimation is a process where you find a direct transformation of solid to the vapor form. So on heating, solid iodine goes to the gaseous form, and on cooling, the gaseous iodine molecules, they again closely packed, resulting in solid iodine. Now focus your attention on the outermost valence electrons that I have highlighted. Now in case of iodine atom, here's the electronic structure of the iodine atom as well as the Lewis dot structure. and two iodine atoms, they share the electron pair, resulting in formation of a neutral iodine molecule with symmetrical distribution of electrons. Now I want my viewers to focus their attention on the outermost valence electrons, because it is the outermost valence electrons that participate in the bond formation. So here's the neutral iodine molecule with symmetrical distribution of electrons. Now, due to the polarizability, high polarizability of the iodine molecule, there is a slight distortion of the electron cloud. So here we are talking about the distortion of the electron cloud in the outermost valence electron. So a instantaneous dipole moment is created due to distortion of electron clouds of the valence shell that is making up the covalent bonds. And as a result, there is clustering of electrons, that is outermost valence electrons, towards one side of the iodine atom, and thereby you see a partial negative charge in one of the iodine atoms and partial positive charge on the other iodine atom. Now the iodine atom, that is where you find the clustering of electrons, it tends to repel the electron cloud on the neighboring neutral iodine molecule. So it repels electrons in the atom of the neighboring molecule, leading to induced dipole. So here's the summary of the discussion so far. That is, the melting and boiling points of halogens are primarily influenced by the size of the halogen atoms or molecules. So the number of electrons and the resulting strength of intermolecular forces. So as you go down the group, there is increase in size of halogens. With an increase in size of halogen leads to increase in number of shells. The increase in number of shells, number of electrons increase, and there is a increase in the polarizability of the halogen molecules. So as you go down the group, there is increase in the strength of intermolecular force, that is the van der Waals forces, from fluorine to iodine. And you find a change in the physical properties of the halogen molecules like melting point and boiling point. That is, the melting and boiling points of halogen increases as you go down the group. And not only that, additionally, you see there is a change in the physical state of halogens. That is, you see a transformation from the gaseous state to the liquid state, and from the liquid state to the solid state, with a corresponding increase in the density. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting video, where I'll be discussing about the chemical properties of halogens. Thank you.